The goal of this project was to create a prototype for a Mars rover that can navigate rough terrain to deliver cargo to a designated location. Specific capabilities of the prototype rover include the ability to navigate to specific sites, the ability to recognize and navigate through obstacles on the path to the cargo drop-off site, the ability to deliver the cargo within a specified time frame, and the ability to transport the cargo to the drop-off site without tipping or falling. To create this prototype, the team was provided with a Pi stack containing a Raspberry Pi, Brick Pi, and Grove Pi. Additionally, a robot kit containing a variety of parts and sensors was provided. Also provided were sensor mounts to allow easier integration of sensors to the prototype and a Pi stack holder to safely incorporate the Pi stack into the robot. The final testing of the prototype occurred on a simulated Mars environment, incorporating obstacles such as rough terrain and sharp turns.
In order to effectively manage the project, Team 26 used many methods of project management. In order for the team to identify the requirements put forth in the project description, the team analyzed the project description document and created a technical requirement chart. With this chart, the team created technical needs and target values that the macro should be able to accomplish. Throughout the design process, which was week 1 through 3, the team visited the technical requirement chart in order to make sure that the macro is on track to successfully complete the demonstration. Before changing or adding something significant to the robot, the team consulted the technical requirements chart. While the team used the technical requirement chart to plan for the completion of the project, the team established meeting goals before and after each team meeting. This allowed for the team to stay on track and tackle the problems that needed to get done at each meeting. The team managed the time frame of the project by consulting a Gantt chart put together at the beginning of the project. The Gantt chart is shown to the right, and it shows the major parts of the project and the time frame of when they are worked on. The team would discuss the Gantt chart and the timeline of the project during each meeting. When the team discussed the Gantt chart, the team would also make adjustments to the schedule when needed. The team decided that 3 weeks was adequate for building the robot, 2 weeks was adequate for coding the robot, and 2 weeks prior to the demonstration were used for testing. When the team met, each member would take on a role, and the timekeeper would help manage the time that the team spent on certain topics, and would make sure that the team had adequate time to hit each of the goals during the meeting. In order to divide the work between the team would put those with the most technical knowledge on a subject to work on that subject. The team discussed each new development on the robot as a group, but worked separately in order to improve the design or the code. The team also established team roles, which would split the job of creating meeting logs, establishing goals, allowing everyone to speak, and keeping track of time during the meeting.
Initially, the team planned to have one motor for the front wheels of the prototype and one motor for the back wheels in order to decrease weight and therefore increase speed. However, to turn, the prototype would have the wheels on one side go backwards while the other side went forwards. These two plans were incompatible, and the team wanted to avoid putting too much stress on the motors considering there were more than 2 available. Due to these issues, the team decided on 4 wheels with 1 motor each in order to enhance turning capabilities. The 4 wheel motor systems comprised the bottom structure of the macro, as the motors were strong enough to support only the weight of the Pi on an incline. The team decided to add a 5th wheel without a motor to act as an extra support. As evidenced in the photo, this structure was very flat and not at all compact. As the team began to test the macro on more rigorous obstacles and add additional cargo, the connections between the motor wheel systems began to break apart and proved to be very weak, despite the additional support that was added to the middle of the prototype. The team altered the prototype to make it taller and stronger in the middle. The altered macro proved to be more stable than the previous prototype and integrated a cargo holder as well as a rotating motor that would be powered to rotate the holder and deliver the cargo. This altered prototype formed more of a triangle shape as compared to a flat rectangle. It was structurally supported by 1 nearly vertical back motor wheel system and 2 nearly horizontal front motor wheel systems. The Pi was suspended between the 2 front wheels. The Hall sensor was attached under the cargo holder. The Hall sensor was later shifted to sit under the Pi holder as it was originally too high off the ground and could not sense a magnet. The single motor wheel system in the back came as a result of adding the cargo delivery motor. Adding this non-wheel motor meant that the Pi had only 3 other motor slots available compared to the previous 4. As compared to having back-wheel drive, the team decided that front-wheel drive would prevent the macro from being back-heavy and also provided more accurate turning abilities. Though some additional slight changes were made, this altered structure of the prototype is the design the team ultimately decided on keeping. Slight changes including rejecting the rotating motor and utilizing a spinning motor to connect to the cargo holder. The connection between the cargo holder and the rotating motor was too weak and did not drop the cargo in the radius accurately enough. Further testing on obstacles led the team to realize the initial wheels that were utilized were too small, so larger wheels were implemented for better climbing abilities. Additionally, the axle that was used to connect the front wheels to the pie case was too long and was preventing the wheels from turning smoothly, so a shorter axle was used. The tires from the rear wheels were removed as they caused too much friction when turning, and a fifth back wheel was added to assist the prototype with climbing obstacles. At this point in the process, the team was still deciding if the color sensor or the line finder would optimize line following. The line finders were ultimately decided upon as more than one could be utilized and the code was more simplistic and easier to follow. The line finders were attached behind the wheels at a height that was low enough to sense a black line, but high enough to prevent getting hit by an obstacle. They were also placed at a width that was large enough so that the robot did not have to be placed perfectly centered over the line and would not have to be constantly adjusting itself, but not large enough that the robot would get extremely off track.
To begin the design process, the team created a functional block diagram including all the available sensors and all necessary processes of the code. Some of these sensors were not used, but having this list of available data was useful later on in the project when an issue arose with line finders on hills. Because they had this list of sensor uses, they were able to come up with using the gyro sensor as a takeover mechanism on hills where the line finders did not really work. The group then created flowcharts for the movement functions of the robot, going forward, backward, and turning. These were then coded as user-defined functions in a file called movement functions, which allowed them to be used throughout the code with ease and made modifications to the base functions much easier. This ended up being useful when the group switched from 4 motors to 3, as the code changes only need to be made in one place. To begin writing the actual code for the robot, the team used a touch sensor. This led them to easily tell if the code told the robot to go forward properly, as it was the most reliable sensor, and they continued to use it as they added new components. For example, when the team switched from using 4 motors to 3, they used a touch sensor to see how this affected the robot's turning, and made appropriate changes in the turning code before trying the robot on the track. This was also used to write the cargo dumping code, as it was much simpler and more straightforward to press a button than to try to work with a magnet and the Hall sensor. Once the team had laid out these base functions for their robot, they wrote a flowchart for the code to be used in the demonstration. They identified line sensors and a Hall sensor as the most important ones, and later would include the gyro sensor as well. At first, they used a color sensor to see if the robot was on a line, but once it was clear the color sensor was very unreliable, they switched to line finders on either side. Throughout the design process, the code flowchart changed in many ways, but the general principles present in the first flowchart were still present in the final flowchart. Throughout the coding process, the team had many ideas about how the code could be improved. Some general criteria for deciding if these code modifications would be included are as follows. First, no major hardware changes should be done to make code modifications work. Second, no editing key code elements for niche issues. And third, changing code should not make the code harder to edit in the future. Some code modifications that were not carried out as a result of these rules include changing turn code to turn sharper by backing up less at intersections. However, this would have required moving the line finders further in, which was not practical. Another possible decision that had to be not carried out was the modification of the turning code that after turning one direction, the other line finder would be turned off temporarily. This was useful for the fork intersection, but changed a fundamental part of the turning code, and thus another solution was found. Some implemented ideas include a counter of magnets passed and a gyro sensor override for line following. By using a counter of magnets passed, the team was able to use the Hall sensor to drop the cargo off properly and create different code for when the robot had gone to the correct drop site, as well as allow it to pass by intersections with magnets. Additionally, this code change was limited in scope, so it did not affect the robot unexpectedly. The gyro sensor code had the robot wait slightly before starting, which then allowed the gyro sensor to calibrate itself. Additionally, the gyro sensor affected nothing unless the robot was going uphill, in which case it overrode the controls and had the robot go forward. Both of these changes follow the 3 key rules for the robot and allowed the team to have a much better final code.
2 line finders provide an adaptable system that allows the prototype to travel efficiently over solid and dotted lines. The line finders are spaced horizontally to keep the line centered underneath the prototype. This is beneficial because if the line ever becomes dashed or dotted, the prototype will still be able to follow it. Additionally, this system is beneficial while traveling over curves in the path. The system was coded so that when a line sensor sensed black, the prototype would turn in the direction of that line sensor. This system was over 95% successful in turning along curves and over 90% successful when turning along dotted curves. A benefit of the prototype's code is the incorporation of different turn functions into the code. This made modifying turns regardless of circumstance much easier and more efficient. Additionally, this code allowed precedents to be set on the occasion that both line finders were activated simultaneously. When the prototype was traveling along a known path, this ability was very beneficial and increased the success of this specific turn on the course from 5% to 75% after the code was edited to give the right turn precedence over the left turn. The prototype's turn radius is something that should be considered while making improvements to this design. Due to the issue involving the number of motors on the prototype that was discussed earlier, the turn radius of the prototype was approximately 12 centimeters. This resulted in a complicated and subjective turn function. In order for the prototype to turn, it first had to activate a line finder, then reverse approximately 10 centimeters, and then turn approximately 40 degrees, and then move forward approximately 10 centimeters. This was a complicated process, which in turn made the turning functions very complicated. Due to the non-zero turn radius, there were many variables that could be adjusted. The time of the turn, the speed of the turn, the distance reversed, and the distance moving forward all affected the way the turn occurred. This made the turn code difficult to modify.
The project concluded with the robot able to complete most of the tasks that it needed to accomplish, as established in the technical requirements chart. The project was finished on time and was presented at the final demonstration. While it was able to accomplish some tasks, there is some room for improvement in the tasks it was unable to accomplish. The code did not work as planned in 2 areas: turning the robot and going up a hill. Due to the turns on the test track being tighter than the team had expected, the turn code would cause the robot to go off track. This could have been fixed by altering the time that the robot turns, backs up, and goes forward. The robot was outfitted with an angle measurement device that was intended to increase the speed of the robot while it was moving up a hill. But this device would not sense the angle, and this was because it was sensing the line on the hill at the same time. The line sensors would take priority over the angle measurement device, rendering the sensors ineffective. In order to fix this issue, it would be possible to make the Raspberry Pi check the angle of the robot constantly before it moves, making it so that if the tilt of the robot changes at all, it would immediately affect the speed of the robot.